This video is for Calc Chapter 2, First Section, Section 2.1. So we're looking at tangent lines. So we're going to start out talking about what a tangent line is and what a tangent line is not. So these are all examples of tangent lines drawn to the curve f of x at a specific point. So you can see right here, this line touches the graph of f of x at that single point. Same thing here, Over here, if you continue this line, it's intersecting the function, but we're just interested in what is happening at point P. So it says, drawn to the curve may only touch the curve one time is not entirely true, because you can see right here it touches down there, but for the point we're interested in, this doesn't affect it. So here's some more. This crosses a line at a single point. That is not a tangent line. It is tangent here. It crosses over here. That's okay. We can still say this is a tangent line at point P. This touches the curve at a single point, but it's clearly not tangent. At point P, this is a tangent line. It looks like it's touching the curve at multiple points, but if you zoomed in, you would see that it's just at a point. It says line L is tangent to the curve C at point P, despite the fact that it crosses the curve out here. So this is one where you'd have to zoom in very closely at point P. Okay, now we did this a little bit in pre-calc. We're going to do it again, where we go through the activity of drawing a secant line and then choosing 2 points that are closer together and drawing another secant line until we get to a tangent. So this says begin with an arbitrary point, which we're going to say is this one right here that we're starting at. And then it says choose another point on the curve that is a horizontal distance of delta x units to the right. So I'm going to go from here. So this distance we're going to call delta x, or change in x. And I'm going to put my y value on the curve, attach the 2 points, and that is a secant line. It says, what is the slope? So, remember slope is y2 minus y1 over x2 minus x1. This point right here, I'm going to call x, comma, f of x. So my y2 minus y1 will be f of x minus f of c over x minus c. So the slope of my secant line will be y2, which is f of x, minus y1, which is f of c, over x2 minus x1. So this is point C, this is point X. Hopefully this is looking familiar to you right now. All right, we're going to do the same thing, just for kicks, like the note says, but we're going to choose a smaller delta x. So I'm going to say this is my x, this is my c. If I go up, there's my tangent line. The slope will be exactly the same. F of x minus f of c all over x minus c. Okay, what's happening here? Since we're having such a blast moving our second x value closer to c, let's move the x value so that it almost touches c. So say like right there. So it's technically still a secant line. It says, do you still see a secant line? Kind of. Mine's kind of drawn on purpose to look like a secant. This says, how could we perceive the slope now using a very important concept from Unit 1? That would be a limit. So what we want to do now is say, well, our goal is to get these 2 points as close together as we can. So the way we want to do that with a limit is we want to say we're estimating the slope of a tangent line. I'm going to sketch a tangent line here just to show you. This would be our tangent line at point C. To estimate that, we want to take the limit as x and c get really close together. Here's c, here's x. So as x gets closer and closer to c, as x approaches c, and then we want to take the slope. Now, this should look very familiar. This is like your limit definition of the derivative that you learned in pre-calc. And I think, ta-da, there it is. Now, at this point in these notes, they're calling it the definition of the tangent line. It is also the limit definition of derivative, because the slope of the tangent line, and you can add that in your notes. The slope of the tangent line is the derivative. I abbreviated. Okay, so this says find the slope of the graph of this, which is a line at x equals 1. Well, first of all, the slope of a line never changes. It's always 2. So hopefully after we do this problem, we'll get an answer of 2. So I'm going to use this formula right here. I'm finding the slope of the tangent line at a single x value, which is 1. So I'm going to do f of x, which would be 2x minus 3, minus f of 1. I'm going to plug 1 into my function, all over x minus 1. So it's going to look like this. The limit as x approaches 1, limit as x approaches c, of f of x, which is 2x minus 3, minus f of 1, which would be 2 times 1 minus 3, all over x minus 1. Okay, that is the limit as x approaches 1 of 2x minus 3 minus negative 1, all over x minus 1, which is the limit, I'm going this way, as x approaches 1. This is plus, so that would be 2x minus 2, all over x minus 1. Your numerator can be factored. Limit as x approaches 1 of 2 times x minus 1. X minus 1 and x minus 1 divide to give you 1. So I'm left with the limit as x approaches 1 of 2. That's because the slope is always 2 for a linear. And so our answer is 2, which we should have gotten, because that is a line, and it doesn't matter where I am on a line, the slope will be 2. All right, this one's a little more interesting because this is not a line. Let me zoom in a little bit here. All right, we're going to do all the same thing. We're also still approaching 1. By the way, because this is the derivative, I'm going to name it. F prime of 1 is the derivative of the function f when x equals 1. So this one I'm going to name it as the derivative. Limit as x approaches 1 of f of x minus f of 1 all over x minus 1. Simplify that. I'm going to skip a step in there. If I lost you, pause the video and figure out the algebra that happened between this step and that step. And then the limit as x approaches 1, factor the numerator. Simplify. Limit as x approaches 1 of x plus 1 equals 2. So on this curve, x squared plus 1, when x equals 1, the slope of the tangent line is 2, or the derivative at x equals 1 is 2. And then this is where we start talking about this prime notation. F prime of c, red, F prime of c, is used to denote the slope of the line tangent to the function f of x at x equals c. So they've taken that limit definition from above and now called it f prime of c. Turn the page and you will see that is a derivative, which I already said and we already called it that. Okay, we have a multiple choice question here. If f is a function for which this is true, so this is the derivative of f at x equals -2 is 0. That's what this means, because this is the limit definition of the derivative. This is our x value. So this means f prime of 2 equals 0. Then which of the following statements must be true? X equals -2 is a vertical asymptote of the graph. This is not true, because if there were a vertical asymptote, then the function wouldn't be defined at -2, and so we couldn't take the derivative at -2. The function is continuous at 2. We don't really know anything about what's happening at 2. We only know what's happening at -2. The derivative of f at x equals -2 exists. Thinking, yes, that's true. That's what I wrote up there. F is not defined at x equals -2. This is false. If I can take the derivative at -2, then the function is defined. So this is C. That is section 2.1.